What if it isn't fundamental? What if it's just, well, an illusion? Not exactly a magic trick, but something that emerges from something much deeper.
That's the big question, isn't it?
Yeah, we're diving into maybe the toughest problem in physics today.
Mm-hmm.
Trying to make Einstein's general relativity with its smooth curves play nice with quantum mechanics, which is all probabilistic and messy.
It's like mixing oil and water, fundamentally.
Exactly. And this idea of emergent gravity offers a pretty radical way to think about it. For this deep dive specifically, we're looking at a framework called the Quantum Vibrational Universe, QVU for short. The idea is basically the universe is just humming with vibrations everywhere at all scales. And an object, what it is, where it is, it's all described by these vibrations.
Right.
And somehow gravity just pops out of how these vibrations interact.
Yeah.
QVU tries to take that cool, intuitive idea and make it actual science, rigorous math and all that.
That's the goal. And for this deep dive, we're really going on a bit of a journey. We'll look at how the QVU model tries to put this into formal language, mathematical language. We'll see how it tries to explain gravity, the force we experience every day, how it handles basic stuff like energy conservation, but also, importantly, what huge questions it doesn't answer yet. Because there are plenty.
Naturally.
So yeah, get ready for some potentially surprising things. Maybe a few aha moments, hopefully. It really is a different way to look at the universe.
Okay, let's get into it. We're talking vibrations. That sounds a bit new agey. How do you make vibration a concrete physics concept in QVU?
Right. It's not just a vague metaphor here. In QVU, vibration is formalized. It's represented by a fundamental scalar field. Think of it like the Higgs field, but for this vibration idea, we call it psi, written as XXT. It pervades all of space-time.
A scalar field, so it just has a magnitude, a number at every point, no direction.
Exactly. Just a single value representing the local intensity or maybe the rate of this fundamental vibration. It's everywhere, influencing everything.
Okay, so if this psi field is everywhere, where do things like planets and stars come in? Are they just floating in the field?
No, not floating in it. The idea is they are the field, in a way. Physical objects are seen as localized, stable excitations of the psi field. Think of them like persistent ripples or knots in the field.
Okay.
And an object's mass, for example, is basically a measure of the energy locked up in that localized vibrational pattern. How intense the wiggle is, so to speak.
I see.
And this actually fits quite well with how we think about particles in quantum field theory already. Particles aren't tiny balls. They're quantized excitations of quantum fields. So it's a similar kind of picture.
That's a really different way to think about matter itself.
Yeah.
Someone listening actually sent in a great question about this. They had this intuition, like maybe objects get closer as their vibrations get closer. It sounds nice, but how does QVU make that scientific?
That's a really interesting intuition. And yeah, QVU formalizes it using the principle of field superposition.
Superposition. Like waves adding up.
Exactly. The total psi field at any point is just the sum of the fields generated by all the massive objects around. And the way these objects move, how they seem to attract each other, that's all governed by the interactions within this combined field.
Okay.
And here's a key point. The model postulates that the gravitational force, Fg, comes from the gradient of this psi field, how steeply it changes in space. Field is proportional to minus the gradient of psi.
Like how force comes from a potential energy gradient.
Precisely. And because it's derived from a scalar potential like this, it automatically means gravity is a conservative force in this model. You get gravitational potential energy built right in.
Oh, okay.
That's actually pretty significant. It lays the groundwork for talking about energy conservation later, which is obviously critical. It's not just tacked on.
So, this psi field, it brings up a huge question, maybe the question for any vibration theory. What's vibrating? Is the psi field vibrating in space-time, like waves on a pond, or is space-time itself made of these vibrations?
That choice is absolutely fundamental. It has massive implications.
How so?
Well, think about it. If the psi field was some kind of stuff, an ether, basically vibrating within a fixed pre-existing space-time.
Right.
Then that stuff would define a special reference frame, the frame where the ether is at rest.
And that violates relativity.
Exactly. It violates Lorentz invariance, a cornerstone of Einstein's relativity that's been tested incredibly precisely. No preferred frames allowed. That's been the downfall of many, many attempts at emergent gravity theories.
So how does QVU get around that?
It takes the radical route. The QVU postulate is that the psi field is not in space-time. Its dynamics define the emergent geometry of space-time.
Oh, okay. Unpack that.
It means things like distance, time intervals, curvature. They aren't fundamental background properties. They emerge from the large-scale collective behavior of this underlying psi field.
So space-time itself is
Yeah.
emergent, not just the force of gravity.
Correct. Space-time is what you get when you average out the behavior of the psi field over large scales.
Wow.
Uh,
That's a mind bender. Does that idea connect to anything else in physics? Or is QVU totally out on its own here?
Oh, it definitely connects. This lines up really well with ideas in what's called emergent modified gravity, or EMG.
Hmm.
There's a phrase sometimes used, space-time is not gravity, but rather it is made of gravity.
Hmm.
By saying the psi field creates space-time, QVU avoids the preferred frame problem altogether. There's no background for it to be at rest relative to the rules of the field or the rules of geometry.
Okay.
So it's much more ambitious than just explaining the force. It's aiming for a theory of emergent space-time itself.
That is ambitious. Okay, let's ground ourselves a bit. How does this whole vibrational picture give us back something we know really well, like Newton's inverse square law, gravity getting weaker with distance squared? How does QVU derive that?
Right, back to the basics. So we said the force Fg is minus mv times the gradient of psi. Fg equals Nash mv. Now, this mv is like a vibrational charge, how strongly the particle feels the psi field.
Okay.
And here's a critical constraint for this to work, for it to match observations and the weak equivalence principle, feather and hammer falling together, this vibrational charge, MAV, must be directly proportional to the particle's inertial mass make.
Ah, the equivalence principle. So it has to assume that for now.
Yes. Right now, it's a necessary postulate. Ideally, a future version of the theory would derive why they're proportional from deeper principles, but for now, we need it.
Got it.
And just as a side note, this whole force from a potential setup is just like electrostatics, right? Electric force from electric potential. It confirms gravity is conservative in this framework.
And that spherical vibration idea we mentioned earlier, does that come into play for the inverse square law?
It's absolutely central to it. It's not just a pretty picture. We model a massive object, like a star, as basically an isotropic point source.
Meaning it radiates outwards evenly in all directions.
Exactly. It's radiating some kind of conserved vibrational energy flux. Think of it like ripples spreading out perfectly spherically. Now, basic geometry tells you what happens next. This energy flux spreads out over the surface of an expanding sphere. The area of that sphere is 4 pi r squared.
Right, gets bigger fast.
Yeah. And if the total energy flowing through the sphere per second has to stay the same energy conservation, then the intensity, the energy per unit area, must fall off as the area increases.
So intensity drops like 1 over r squared.
Precisely. Just like light from a bulb or sound from a speaker, intensity all is proportional to 1r2. That's just geometric dilution in 3D space. Okay, now connect that to psi. In pretty much any wave theory, the intensity of the wave is proportional to the square of the wave's amplitude. So if we identify the amplitude of our fundamental psi wave with the value of the scalar potential, psi itself, then intensity I is proportional to psi squared.
Ah, I think I see it coming. You've got intensity going like 1 over r squared from geometry.
Yep.
And intensity going like psi squared from wave physics.
Exactly. Put them together. If I is proportional to 1r2, and I is also proportional to A2, then A2 must be proportional to 1R2.
So psi itself is proportional to 1 over r.
Right. The potential falls off as 1R. Now, plug that back into our force equation. Fg equals, instead of ms, mg. What happens when you take the gradient of 1r? You get something proportional to 1r2, pointing radially inward.
The inverse square law.
It just pops out. It's an inevitable consequence of assuming a conserved energy flux radiating spherically in 3 dimensions.
So QVU isn't just assuming Newton's law. It's arguing it has to be that way because of energy conservation and geometry in this vibrational framework.
That's the claim. It suggests the inverse square law isn't some fundamental rule handed down from on high, but an emergent property of this deeper vibrational reality. That's a profound shift in perspective if it holds up.
It really is.
Okay.
But how does this position QVU against the giants, like Newton and GR? Is it just finding a new way to get the old results, or does it offer something genuinely different? Where does it fit in the landscape?
It's in a unique spot. It's not classical like Newton, not purely geometric like GR. It does share that emergent flavor with things like entropic gravity, the idea that gravity and space-time aren't fundamental.
Yeah.
But it differs fundamentally from entropic gravity because QVU postulates a physical thing, the psi scalar field, as the underlying reality. Entropic gravity talks about more abstract concepts, entropy, information, temperature.
So QVU has a more concrete stuff behind it, even if we don't know what that stuff is yet.
Exactly. And this sort of hybrid nature, using a classical-looking mechanism, the gradient of a potential, to explain a phenomenon emerging from a quantum-like substrate that's both its potential strength, bridging worlds maybe, but also a source of its biggest challenges, as we'll get to. It's trying to sit between different paradigms.
Okay, speaking of challenges, conservation laws. You mentioned energy conservation earlier. How does QVU actually explain something basic like an object falling? Where does the kinetic energy come from as potential energy decreases? One listener asked if it involves changes in vibrational states.
That's exactly the proposed mechanism, and it's quite speculative, but it draws on a fascinating analogy from quantum physics,
Oh, fun.
the Franck-Condon principle. It comes from studying how molecules absorb or emit light spectroscopy.
Okay, how does that work?
The core idea is that electrons in a molecule move much faster than the heavy atomic nuclei. So if an electron jumps to a different energy level, an electronic transition, it happens almost instantly from the nuclei's point of view.
They don't have time to react.
Right. The nuclei find themselves in their old positions, but now in a new potential energy landscape created by the rearranged electrons. They might suddenly be in an excited vibrational state within that new electronic potential. Well,
So the electronic change triggers a vibrational change.
yes. And then the molecule usually relaxes, maybe by vibrating or eventually emitting energy, to settle into the lowest vibrational state of that new electronic level. Energy gets redistributed. Now, map that to QVU and gravity.
Let's try.
The molecule's electronic state is like the falling object's position in the gravitational field that determines its potential energy, UR.
Okay, the potential energy landscape.
The molecule's vibrational state is like the falling object's internal vibrational state. We imagine the object itself has some kind of quantized internal vibrational energy levels related to its structure within the psi field.
Eternal modes, right?
And that vertical transition, the sudden electronic jump, is analogous to the act of falling, where the object rapidly experiences a changing external gravitational potential, UR.
Okay, so walk me through it. An apple starts falling. What happens according to this analogy?
Right. Step 1, initial state. Apple at rest, high up. Total energy is its potential energy, high, plus some initial internal vibrational energy, EVIB, initial.
Got it.
Step 2, the fall. As it moves closer, its potential energy U decreases rapidly. Step 3, the vibronic transition. This rapid change in the external potential U induces a transition in the apple's internal vibrational state. Crucially, the model proposes it transitions from a higher internal energy state to a lower internal energy state. It de-excites internally.
It dumps internal energy.
Yes. Step 4, energy conservation. The energy released from this internal de-excitation, let's call it delta EVIB, is transferred to the object's overall motion. It manifests as microscopic kinetic energy.
Whoa! So the kinetic energy doesn't come directly from the potential energy field, but from the object's internal energy store triggered by the change in potential.
That's the proposed mechanism. The change in internal vibrational energy mediates the conversion of potential energy into kinetic energy. It's an indirect process.
That is really different. Is there anything remotely like that? Observed experimentally, this idea of motion coupled to waves or internal states?
There are some fascinating analogies. You might have seen videos of the walking droplets experiment.
The ones bouncing on vibrating fluid.
Yeah, exactly. Those experiments show empirically that a droplet, the particle, can have its trajectory, its kinetic energy, strongly influenced by the wave field it creates in the vibrating fluid bath. There's a feedback loop.
Okay.
It's not a perfect analogy, obviously, but it's a sort of proof of concept that particle-wave feedback loops can govern motion in surprising ways. It gives a conceptual handhold for the QVU idea.
Interesting. And what about momentum? Does this internal transition idea mess with Newton's third law?
Good question. No, the model handles that too.
Okay.
The falling object, remember, also generates its own little contribution to the psi field.
Right, it's an excitation too.
So that little field creates a tiny gradient back at the source mass, like the Earth. This results in a reciprocal force tiny, but equal and opposite. That's QVU's version of the third law.
Okay, so action-reaction still hold.
Yes, total momentum is conserved. That kind of reciprocity is essential for any consistent field theory. And maybe even more speculatively, the fact that this involves distinct timescales and internal state transitions, it hints that gravity might not be perfectly smooth.
Like quantized, jumpy.
Potentially. Maybe gravity happens in tiny, discrete, quantum-like steps or events. If so, that could lead to testable predictions, maybe tiny fluctuations in gravity, or specific selection rules for how these energy transfers happen, things GR wouldn't predict.
Hmm.
And it might also help with the problem facing entropic gravity theories. Those often imply gravity should be a noisy statistical process that breaks quantum coherence.
Which experiments suggest isn't happening, right? Gravity seems to preserve coherence.
Exactly. But if the QVU mechanism is more like a coherent quantum transition, like the Franck-Condon analogy suggests, maybe it could preserve quantum superposition during gravitational interaction. That would be a huge point in its favor.
Okay, so we've seen how QVU tries to build a picture, reproduce known laws, handle conservation. But now, the reality check. What are the really big, maybe show-stopping challenges QVU has to overcome to be taken seriously?
Oh, the challenges are immense. Absolutely formidable. First and foremost, what is the psi field?
Yeah, the elephant in the room.
Is it some totally new fundamental scalar field we've never detected? If so, how does it interact with all the particles and fields? We do know the standard model stuff. Does it couple to quarks, leptons? How? Or is psi maybe not fundamental but emerges from something else we know? We just don't know.
That's pretty fundamental. What else?
Relativistic consistency and the equivalence principle. We talked about needing the vibrational charge mv to be proportional to inertial mass m.
As a postulate.
Right. But why? A mature theory needs to derive that proportionality from first principles. It's the absolute bedrock of general relativity, why everything falls the same way. Just postulating it isn't enough in the long run. QVU needs to explain why it's true. Then there's maybe the biggest theoretical hurdle, the scalar to tensor problem.
Sounds technical.
It is. QVU, as we've described it, gives you gravity as a force derived from a scalar potential, psi, effectively acting in flat space.
Okay.
But general relativity describes gravity as spacetime curvature. And curvature isn't a scalar. It's described by the metric tensor, beam. That's a much more complicated mathematical object with 10 independent components at each point in spacetime.
And psi is just one number at each point.
Exactly. How can one single scalar field, psi, possibly dictate all 10 components of the metric tensor? It seems impossible. You don't have enough information in the scalar field.
So the basic QVU setup can't fully reproduce GR's geometry.
Not in its simplest form. It suggests the underlying stuff of QVU might need to be more complex than just a single scalar field. Maybe it needs to be a tensor field itself or have multiple components.
Yeah.
This connects directly to ongoing research in things like emergent modified gravity, trying to figure out how geometry emerges. It's a huge gap to bridge.
Wow. Okay, what else is on the list?
It's quantum nature. If psi is fundamentally quantum, how does this energy exchange work? Is it a smooth, coherent process that preserves quantum superposition? Experiments with, say, ultra-cold neutrons falling in gravity suggest gravity is coherent.
Right.
Or is the QVU process more statistical, noisy, dissipative? That would lead to decoherence, washing out quantum effects, which seems contrary to observation. The details of its quantum behavior matter enormously. And finally, the big cosmological questions: dark matter and dark energy.
Can QVU explain them?
Well, for it to be a truly universal theory, it would need to. This would likely require the psi field dynamics to behave differently on very large scales, galactic or cosmological scales. Maybe the field has nonlinear self-interactions that become important over vast distances or high densities.
Like MOND theories try to do.
Yeah.
Modify gravity on large scales.
Potentially, yes. QVU would need to show how its fundamental equations naturally lead to effects that look like dark matter in galaxies and dark energy driving cosmic acceleration without actually needing mysterious new particles or energies. That's a tall order.
Understatement. Okay, so with all those massive hurdles, what's the path forward? If someone wanted to develop QVU seriously, what are the concrete next steps?
You need to build the formal machinery. First step, develop a proper Lagrangian formulation.
The master equation.
Kind of, yeah. For physicists, the Lagrangian density is the starting point. It encodes the field's kinetic energy, potential energy, how it interacts with matter. If you have the Lagrangian, you can, in principle, derive everything else about the field's behavior using standard techniques.
Okay, write the blueprint, then what?
Use that Lagrangian and the principle of least action, a fundamental concept in physics, to derive the actual field equations for psi.
The equations of motion for the field.
Exactly. These would be the QVU equivalent of Einstein's field equations for general relativity. They would tell you how matter sources the psi field and how the psi field evolves over time. These are the core dynamical laws you need.
Makes sense.
And then, critically, the theory absolutely must make unique, testable predictions. predictions that differ from general relativity or other competing models. Otherwise, it's just redescribing things we already know.
Where might those predictions come from?
Maybe tiny deviations from GR in extreme places, like near black holes or in the very early universe. Perhaps gravitational waves would look different. Maybe psi waves have different polarizations or propagation speeds that LIGO, Virgo, or future detectors could spot. Or, as we mentioned, it needs to make specific quantitative predictions about dark matter and dark energy, like predicting the exact rotation curves of galaxies or how the cosmological constant should behave over time. It needs to stick its neck out with things we can actually go and measure. That's the only way to really test it.
So wrapping this up, the Quantum Vibrational Universe, QVU, it's this really fascinating, almost intuitive picture of emergent gravity.
Yeah.
We've seen how you can formalize its core ideas, how it actually derives Newton's inverse square law as this necessary consequence of energy flow.
Yeah, that part is quite elegant.
And how it offers this, speculative but plausible mechanism for energy conservation
Yeah.
using these internal vibrational state changes.
Yeah.
It's definitely a bold, different way to think about gravity, suggesting it's not fundamental, but emerges.
But, and it's a huge but, as we've laid out, QVU is really just at the starting line. The theoretical obstacles are immense. Getting relativistic consistency, explaining the equivalence principle from scratch, solving that huge scalar to tensor problem to connect with GR's geometry, figuring out its quantum coherence properties.
Not to mention dark energy and dark matter.
Exactly. These are grand challenges. Overcoming them would require major breakthroughs, potentially redefining fundamental physics. It's a long, long road ahead.
So we'll leave you with this thought to chew on. What if our universe isn't fundamentally about particles and forces in a background space-time? What if, at its deepest level, it really is a kind of cosmic symphony, a universe of quantum vibrations, and gravity, the most familiar force, is just one of its emergent melodies, an echo of that deeper vibrational reality? It's a difficult path, for sure, but exploring it offers a completely fresh perspective on gravity, space-time, and maybe the universe itself, something definitely worth thinking about.